We start off by taking a look at the graph of log x, and in particular, log x and 10 to the x. Recall f at x equals 10 to the x, and log x, which is actually its inverse, so we'll call it f inverse of x equals log x, represent a pair of inverse functions. We also know that f at x equals 10 to the x is an exponential growth graph. Notice, by the way, if I just graph 10 to the x, which you can see on the graph down below on the screen, that it passes the horizontal line test. It also passes the vertical line test because it's a function. So f is 1 to 1, and therefore it's invertible. One of the ways we said before we could actually graph an inverse was either by interchanging the x's and y's, or by graphing the function by reflecting it over the line y equals x. Well, notice if I look at this graph, if I actually look at y equals 10 to the x, and I draw the line y equals x, which is the line that you see going through quadrant 1 and quadrant 3, that if I reflect y equals 10 to the x over that y equals x line, I get another graph, and that graph is in fact the log x graph. So now if I take a look at those graphs, I can notice a few items. So let's just take a minute and take a look at this graph, and then we'll actually talk about the summary. So again, my y equals 10 to the x is an exponential growth graph. Notice it rises very quickly once it passes to positive x values, and it falls rather quickly. It looks like it approaches the x-axis when we get off into the negative x values. Notice if I take a look at the log x, it has kind of a similar behavior. Instead of approaching the x-axis, it approaches the y-axis, and instead of getting really steep along or near the y-axis, it gets very steep. The log x gets very steep, as you might call it. Almost looks like it flattens out, if you want to think of it that way, along the x-axis. So now let's take a look at a few items that relate these two together. So if I have the function 10 to the x, the domain, the legal values of x, are all real numbers, right? And if I take a look at that graph, the range are all of the y's that are greater than 0, or in other words, everything from 0 to infinity, but technically not including 0. Even though it looks like it makes it down there, remember it gets very, very close. So in other words, the range, the y values for 10 to the x are the positive reals. Notice also this has an asymptote, and the asymptote of 10 to the x, as we talked about before, would be y equals 0. Now let's take a look at log x, and we'll notice a few things. We'll notice when we look at log x that the domain is the positive reals. So the values of x that are greater than 0. Notice, as we said before, the domain and the range get interchanged when we have inverses, and so notice the domain of log x is actually the range of 10 to the x. Notice the range of log x is actually going to be everything from negative infinity up to positive infinity. Even though log x doesn't look like it grows terribly quickly, it will keep getting larger and larger and larger and larger. And so the range of log x is all reals, which corresponds to the domain of 10 to the x. Log x also has an asymptote, except its asymptote is now the y-axis. It's now the equation x equals 0, similar to the asymptote for 10 to the x. 10 to the x had an asymptote that was y equals 0. Log x has an asymptote which is x equals 0. Notice, by the way we get the asymptote on the log function is it actually can be generated by thinking about what value or values makes the inside of the log function, in this case the x, equal to 0. So it's x equals 0. If that had been more complicated, we would have just taken that input area, that stuff that's inside the parentheses, and set that equal to 0, and that would have given us the asymptote for the new and improved function.